Hey everyone, this is Greg from ChemCore. In this video, we are going to be going through the Isomers worksheet. If you haven't had a chance to check out this worksheet, it is in the description below, as well as the answer key. And if you're unfamiliar with the concepts in this video, there is an instructional video, the topic video, also linked below. Before going through the problems, I kind of want to establish that we have, at this point, two different types of isomers. We're going to learn a lot more isomers throughout this course, actually, I think in this chapter as well. But for now, we only know two forms. Now, constitutional isomers pretty much are saying that we have the same molecular formula. So the same molecular formula. But different structures. And so let's establish that before beginning this video, because that's going to be an important concept. And Cis-Trans is going to talk about double bonds, so double bonded carbons, in which we have something like this, is cis, while the groups facing away from each other are trans. And then in the instructional video, I also mentioned a little tidbit that almost seemed unimportant about the fact that sometimes, even though you have a double bond, it might not be neither cis or trans. It might be, none of them. And later in this worksheet, we're going to see examples of that in which I stress it for a reason. The first problem, though, is asking us about constitutional isomers. Now, the best way I can the foolproof method of doing this is, well, let's figure out what is the formula for each structure. If the formula is the same, but the structure is different, we know we have constitutional isomers. And so the first one, we have 1, 2, 3, 4, 5 carbons. 5 carbons. Let's clean up. Let's count how many hydrogens we have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 hydrogens and 1 bromine. In the next structure, I see 1, 2, 3, 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. And again, 1 bromine. The next structure 3, I have 1, 2, 3, 4, 5 carbons. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hydrogens. And again, 1 bromine. And in the last structure, I see 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hydrogens again, and 1 bromine. And so we realize that, well, 3 of these structures have the same molecular formula. One of them does not have the same molecular formula, so we can definitely wipe out structure 2. That's definitely not part of the constitutional isomers. But, just because they have the same formula doesn't mean that we can automatically group them as isomers. The issue is that they must be different structures as well. And so visually looking at this, this one, structure 1, is definitely quite different from structure 2. And structure 4 is also pretty different. And so I can safely say that structures 1, 3, and 4 are all constitutional isomers. Now, question 2 is giving us 2 formulas, and they're asking us, what are the examples of? Well, the thing is that I didn't teach you guys conformational isomers yet. That's a topic for later in this unit, so we can remove that from the answer choices. Resonance structures, we know what that is. Functional isomers, did I ever mention functional isomers? We did not. Did I ever mention empirical isomers? That's not a thing either. And so now we have to realize, are they constitutional isomers or resonance structures? And I always repeat to my students, when in doubt, draw it out. In fact, even when you're not in doubt, you should still be drawing it out. And so the first structure, let's try drawing it out. It's going to look something like this. And our next structure will have 4 carbons, again, 1, 2, 3, 4, and an oxygen at the end. Well, clearly they're not resonance structures, right? Like very clearly, for many, many reasons, there's a big change in atom structure, and where the atoms are connected, clearly they're not resonance structures. And the fact that they are, different arrangements of atoms is exactly our definition of constitutional isomers. We have a different arrangement of the actual atoms themselves. And so these two structures are constitutional isomers. In the next problem, we're again looking for compounds that are constitutional isomers of each other. Best way to again do it, let's figure out our molecular formula for each. And if some structures have the same molecular formula, but they look different, well, we know that they're constitutional isomers. And so the first structure has 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 carbons. Structure 2, 1, 2, 3, 4, 5, 6, 7. Again, 7 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Again, 16 hydrogens. Structure 3, 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hydrogens. And then structure 4, our last one, 1, 2, 3, 4, 5, 6, 7. 7 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Structure 4 has a very different molecular formula. Well, not very different, slightly different. But no matter, it still has a different molecular formula than the other 3. And so we can definitely wipe this out. This would not be related as a constitutional isomer to the rest of the group. But I know that, okay, you see that these 3 have the same molecular formula, but that doesn't automatically mean that they're constitutional isomers. They must also have the same structure. So if we clean it up a bit with all our marks, let's make sure. Well, yeah, visually, I mean, you don't even have to look twice. They're very different, right? The arrangement of the carbons are very different. And so we can safely say that structure 1, 2, and 3 are all constitutional isomers. In question 4, again, we're trying to figure out something with constitutional isomers, but in this one, we're trying to figure out which one is not the constitutional isomer of the others. Now, I know these structures must look complicated. They look complicated, but they're really not. Again, our strategy is the same. Let's figure out the molecular formula, and then we can, well, if one of the molecular formulas is clearly different, that would be not the constitutional isomers of the rest. And so the first structure, let's just draw this. This is a CH2 over here. I see 1, 2, 3, 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens, as well as an oxygen and a nitrogen. Now, I know this must look weird. It doesn't matter, right? For our purposes, it doesn't matter how our structure looks. Carbons, 1, 2, 3, 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens, and then an oxygen and a nitrogen. Structure 3, 1, 2, 3, 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, 9 hydrogens, and an oxygen and a nitrogen. I mean, you can pretty much assume that your last structure is not going to be the constitutional isomer, but let's just make sure. 1, 2, 3, 4 carbons. 1, 2, 3, 4, 5, 6, 7. Only 7 hydrogens, and then an oxygen and a nitrogen. And so the only structure that's different from the other 3 is structure 4. In the next problem, they're asking us to find which of these 2 structures represent the same compound. To do this, the best way, I think, is when in doubt, draw it out. I don't like structures like this. This is not the way the way organic chemists look at compounds and organic molecules. And so let's try drawing them out in our bond line structures. Each of these structures has 1, 2, 3, 4, 5, 6 carbons. This is structure 1. And so we have a double bond between carbon 3 and carbon 4 in the first one. Structure 2 is going to have a double bond between carbon 2 and 3. Structure 3 is going to have a double bond between, well, up to the last carbon. And structure 4 is going to have a double bond on the first carbon. Now, apologies, I numbered the structures wrong. Had to switch 2 and 3. But what you're realizing here is that this structure is really the same as structure 4 if I were to just flip the molecule around. And so I can say that structure 2 and structure 4 are really the same compound. In the next problem, they're asking us which of the following represent a pair of constitutional isomers. To do that, my strategy is let us draw or write out the molecular formula for each and then determine each individually. So the first one, we're getting two structures. Clearly they look different. Do they have the same molecular formula though? Well, the first one is carbon 3, so it has 3 carbons. It's 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. And the second structure, C3, 1, 2, 3, 4, 5, 6. It has 6 hydrogens. Clearly not the same molecular structure, and so we know that these are not constitutional isomers. In the next problem, we've been given two structures that are not really a bond line, so let's try to draw them out. It would look something like this, with no particular order. Now realize that these are not isomers. They're literally the same compound, just flipped over. And so we can't say that these are constitutional isomers. The next structures, they drew it out for us, and so we can just consider it like this. Remember, this is where we start talking about double bonds. Notice that we now have a double bond that have two different groups on each side. Now, the important thing to remember is that double bonds cannot move. Whatever way they are drawn is the way they are. So if you remember my fist example from the topic video, you'd realize that. Notice that in this pair, the arrangement of bromines are actually different. So you can compare these two bromines. And so we can't just, it's not just up to drawing. It's actually the way they're arranged. They're actually on completely different carbons. And so we can't say that these are cis-trans isomers. They're literally placing the bromine onto a different carbon. And so we can't say that these are constitutional isomers. And the same story is with the other one. Look at these two bromines, right? They're not even on the same carbon. They're placed onto entirely different carbons. And so we can say that this is a constitutional isomer as well. And so our answer choice would be E, more than one of these choices. In the next problem, they're asking us which of the following represents pairs of constitutional isomers. My strategy remains the same. Let's write out the molecular formula and see if it's the same or different. So the first structure, we have 1, 2, 3, 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and 2 oxygens. In the next structure, I see 1, 2, 3, 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and again 2 oxygens. And so these are constitutional isomers. In the next pair, notice that again, this bromine is just on a completely different carbon. And so this does not count as cis-trans isometry. This bromine was literally placed on a different carbon. And so we can say that yes, this also is a pair of constitutional isomers. In the next structure, this might look, a little annoying, a little weird, but realize they're just trying to trick us with the structure. It's really just saying something like this. And so we can kind of redraw the structure like this. So H, then H, and then CH3, then Br. Okay, and now notice that this bromine could have stayed the same, but this carbon, this CH3, was put onto a completely different carbon. And so we can say that this also is a pair of constitutional isomers, meaning that our answer is E. All of these pairs are constitutional isomers. The next problem is asking us which of the following compounds is not a constitutional isomer of the others. Well, best option, again, let's calculate the molecular formula. So first problem, we have 1, 2, 3, 4 carbons. 1, 2, 3, 4, 5, 6 hydrogens, and an oxygen. In number 2, I see 1, 2, 3, 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. and an oxygen. Number 3, I see 1, 2, 3, 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens and an oxygen. And example 4, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens and an oxygen. And clearly we see example 1 is not related to the other 3. And so example 1 is not a constitutional isomer of the others. In this example, again, we're trying to find out which one of these is not a constitutional isomer of the others. Now, in the past couple examples, we've used the molecular formula, literally calculating one by one to figure out which one is not the same molecular formula. In this one, I kind of want to use a different technique. Let's try to figure this out visually. And so if we visually try to compare these first two, we'll see that, well, we have this kind of ring with 3 double bonds and 2 OHs. Now, it's the same, right? It's the same on this structure. We literally just have an OH. And so these two are definitely constitutional isomers, meaning that one of these must be different. And so clearly they are quite different. If we compare structure 3 to structure 1, what we'll notice is that we kind of removed this double bond and then added one over here. And now you might think that, okay, that has to be different, but it actually isn't. What we're basically doing is we're kind of moving this double bond. We can almost imagine it kind of like a resonance, but not really, because we are moving a hydrogen. We can almost imagine it like we're switching this double bond for this hydrogen. And that means we're not really changing the count of any hydrogens or carbons or oxygens. And so number 3 is also a valid constitutional isomer. The problem with number 4, though, is that if we try to use the same logic and move one of these double bonds down and kind of bring one of these hydrogens up, we'd only be left with 1 double bond in the ring. But we're still left with 4. How's that possible? Well, I mean, it is possible, but not if it's a constitutional isomer. And so we could say that compound 4 is definitely not a constitutional isomer of the others. Question 10, I'd love to do this visually, but personally, I don't even want to try. I mean, there are a lot of really complicated structures over here. It's really hard to look at them. And I think, honestly, the best option, worth your time and ease of mind, is just to calculate the molecular formula. And I've used this method for, many problems. I think almost 10 problems at this point. So, or 9 problems, because we didn't use that for the previous one. So I'm going to go ahead and just speed through these and calculate the molecular formula. And if you have any differences, make sure to go back and check your work. And so after calculating the molecular formula, we'll realize that structure 3 is the only one that does not have the same molecular formula as the rest. And so we can say the answer is C. Now, in question 11, I did want to include some questions using some concepts that we talk about in the future. So if you haven't yet been able to study or watch my videos on the functional groups, do not do the next 2. We're only going to do the first 2. Don't do the ones that are labeled ketones only and primary amines. I'm going to talk about these problems. You can skip forward. I'm going to talk about these problems assuming that you already know what a ketone and primary amine is. And so for the first one, we're kind of given this formula, C3H8O. Now, these problems are kind of unique. I kind of have a strategy when tackling these kinds of problems. I'm going to try to draw the first structure that comes to mind. So the first structure that really comes to mind is, well, let's just draw these 3 carbons kind of straight. And let's try to add an oxygen and see where we can go from there. And so if you were to count the hydrogens here right now, you'd realize we were missing one. And so one way we can fix that is really just by adding a hydrogen over here. And now to draw all the possible constitutional isomers, what the best strategy is let's try to move this or any of these atoms or carbons or oxygens around to form unique structures. And so what I can do is I can really just move this over here. Let's move this over to the next carbon. And so what we'll end up with is something like this. And that's very unique, right? That's completely different. Now, what if we were to move it one more, all the way to the end? What we would end up is something like this. Now, the issue with this answer is that these are exactly the same. And this is the really tricky part about drawing constitutional isomers using, just vision and trying to draw new structures is the fact that you're going to get some that are identical. The way you can do that is, well, what if I were to look at it differently from either left to right or right to left, or just flip it? Would it be the same structure? And if I were to flip it, just mirror it, it would be this. And so we know now that this is not a constitutional isomer. And so to check the first constitutional isomer that we drew, there's no way that you can really mirror this structure to get this. And so we know that this is a valid constitutional isomer. We have possibly one more. We drew all the ones with the OH kind of sticking outside, but what if we were to draw it with the oxygen inside? What if we were to draw something like this? Now, this is completely possible, right? If you counted the hydrogens, you'd realize that we were left with 8. Now, to try it out, what if we were to kind of switch this oxygen over here, kind of make it like this? Well, now if you were to look at it, this is kind of the same thing. These are not kind of, these are actually completely identical. This is the same structure as if you were to look from left to right. And so this is not a constitutional isomer. And so we're left with only 3 possible constitutional isomers. The next problem, I'm really just going to use the same strategy. Let's draw the first structure that comes to mind. So the first structure that comes to mind is really 3 carbons. And let's just attach all the chlorines to 1 carbon, right? Something like this. Now, all of the remaining constitutional isomers will really just be us kind of moving these chlorines in some combination to other atoms. The first idea that I can do is let's move this chlorine all the way to this carbon, so to the middle carbon. And so what we'd have is 2 chlorines left on the rightmost carbon and 1 chlorine in the middle. Now, another thing we can do is, well, let's just move the other chlorine to the middle. And so what we'd have then is 1 chlorine left at the end and 2 chlorines in the middle. And now the final isomer that you'd really be able to get is, well, let's move one of these chlorines all the way to the end. And so we'd be spread out across 3 carbons. So 3 chlorines kind of spread out like so. And there's no other combinations that you can possibly make with these structures that would give you a completely unique molecule. Now again, before we start this problem, if you haven't learned what a ketone and amines or in general functional groups are yet, do not do these problems, just skip forward. Now to remind you, a ketone, the general formula of a ketone is something like this. And so having this in our top right corner is probably going to help us remember how to draw the ketone. And so the first structure that comes to mind is, well, let's draw all these 4 carbons and just put an oxygen right in the middle. Now the problem with this is if you were to count the hydrogens, you'd actually have 1 extra. And so what we'd have to do is we'd have to give a double bond to one of the carbons. So let me make that a little cleaner. Now realize that by missing 1 carbon, or by missing 1 hydrogen, 2 hydrogens, or giving a double bond, we'd really be doing the same thing as just making it a cyclic structure. And so if we were to make it a square, we would also kind of lose 1 hydrogen or a pair of hydrogens. So if we were to count the hydrogens here, we would have, again, only 6 hydrogens. And there's one more possible structure, again, a cyclic molecule, in which we would have something like this, and then the ketone hanging off one of the carbons, and then the extra carbon, the 4th carbon, as a methyl group attached to the triangle, or the cyclopropane. And now if we look at all these structures, there's no other way to arrange it. There's no way that we can move this double bond to any of these other carbons without breaking the octet rule. Now in the next problem, to remind you, a primary amine, the general formula is something like this. And so something useful to keep in mind when we're trying to draw our constitutional isomers. The first structure that comes to mind is, let's just draw our 5 carbons and then a amine sticking off the end. And so our job now is, let's try to move this amine or this nitrogen around as much as possible. And the first isomer that I can really draw is, let's just move this amine 1 carbon over. And so what we'd end up with is something like this. And let's just keep that going. Let's move it another carbon over and have it right in the middle. It would look like this. And these are all primary amines. We're still in good shape. Now there's still some more structures possible. What if, instead of moving the amine, what if we moved one of the carbons? So what if we move this edge carbon over in order to form something like this? So what if we were to have something like that? Well, that's still definitely possible. And what if we were to move it one more carbon over. We would have something like this. Now, another isomer that we can draw is what if we were to move both carbons kind of to the carbon bearing the nitrogen. And what we'd end up with is something like this. In the next problem, we are tasked with identifying each of the following as either cis or trans or neither. In the first problem, I see two groups that I can compare. So this methyl and this methyl, and they're clearly both facing the same side, meaning that this is the cis isomer. In the next problem, I actually see two groups right over here that I can compare, these hydrogens and hydrogens. It actually doesn't matter that these carbons are not identical. All we need is one group that we can compare. And since they're facing opposite sides, we can call this the trans isomer. In the next problem, realize that we have these two groups that we can compare that are exactly identical. And so since they're facing the same side, we can identify this as the cis isomer. The next structure is trying to trick you. You're going to see these bromine and chlorine and be like, hey, we can compare. We don't have any identical groups. But you do. They're just not drawn. You have these two hydrogens that are facing the same exact side. And so we can call this isomer the cis isomer. In the next examples, we're trying to figure out whether these structures can have cis-trans isometry. And if they do, draw out the cis and trans isomer of each. And to figure this out, the best way for me to do this is really let's draw it out. So it would look something like this. So we have 1, 2, 3, 4, 5, 6 carbons. And we have a double bond from the second carbon to the third carbon. And now after doing so, after looking at this double bond, let's try to find one group on each side of the carbon that we can compare. Now these alkyl these carbon chains on each side are definitely not identical, so we can't compare them. What we can compare are the hydrogens. And so even though we usually don't draw them, they're still there. Now notice that since we can't compare the hydrogens, we definitely do have cis or trans isometry. And actually the isomer that we just drew is the trans isomer. And it's really good practice drawing this trans and cis isomer within a carbon chain. The cis isomer is going to look something like this. 1, 2, 3, 4, 5, 6. 6 carbons, and it's going to look like that. And notice that our hydrogens are again going to stick out, but now it's going to be on the same side. In the next structure, let's try the same strategy. Let's draw out the structure. So we'll have a double bond from the second carbon to the third carbon. And now it's even easier to see that we have these carbon chains that we can compare on each side. And so since we definitely do have cis-trans isometry. And the structure that we just drew is the trans isomer. And to draw the cis isomer, you kind of draw it like a little trapezoid, half a trapezoid. And that would be the cis isomer. Now in this problem, let's try drawing it out. We have these 3 carbons, and then it connects to another 2 carbons, and we have a double bond from the third to the second to the fourth, and then we have these 2 more carbons hanging off. Now, they gave you the specific structure to see if you can really identify whether we have identical groups or not. And at first glance, you might think that these 2 carbon chains are the same, but they're not. We don't have any hydrogens on this side to compare to the hydrogens on the other side. We don't have any groups to compare at all. And so we actually do not have cis or trans isometry. And so we can kind of cross this out. We won't. We'll leave it there. But we do not have cis or trans isometry. In the next structure, we have 4 carbons with a double bond all the way in the end. And now notice that we have these hydrogens hanging off here. We have 1 hydrogen coming off here. And now notice that we have these hydrogens that are opposite to each other. And so you'd be tempted to say that we have cis or trans isometry. The problem is that, well, we have 2 groups on the same side. We have hydrogen and hydrogen. And so if you wanted to compare and say whether it was cis or trans or not, which hydrogen do you look at? You actually don't know. And so this does not have cis or trans isometry. This is one of our examples in the topic video of molecules that would not have or not exhibit cis or trans isometry, in which one of the double bonded carbons has the same group bonded to it. This concludes our worksheet for the isometry video. If you're feeling unfamiliar with these concepts, go back to watch my topic video and maybe retry the worksheet on your own time. and I will see you in the next video.